P.
So friends, we are live on YouTube now. So good morning and welcome everyone. As you already know, our topic is combustion and flame today, and we will be doing some very interesting experiments. So let's begin. SAS group. It will be nice if I can see your faces. So right. So okay. So I'll share my screen. This session is being brought to you because of financial assistance from IOCL, Indian Oil Corporation Limited. And as usual, we'll be asking you a lot of questions. So please answer on chat. Or maybe we can make it verbal because the number of participants is not large. So you can maybe speak. So I will allow you to unmute. Just a second. Yeah, you can unmute. You can unmute. So let's begin. So we have to talk about fire a lot. So we see fire in one form here, very familiar to us in our households. And here's another form of fire. So my first question is to you that here we see fire in a very useful form. And here we see it in a very destructive form, right? So the question is, what makes fire so useful, but also so destructive? It can be very, very destructive. We know that. So what are the qualities of fire because of which it can be our friend, but also our foe?
Depends upon the undesirable material which the combustion.
Depends on what?
Depends upon the undesirable material.
I didn't get your word. Maybe you can type. So Khushi is saying it can be controlled. Yeah, so well, we did control it here, but I am asking you, the question is, I mean, either we can control it, but sometimes it gets uncontrolled. But what is the quality fire has? There's something about fire which makes it extremely useful, but also very destructive. So, okay. So Dory is saying the material which is being burned, the material which is being burnt, there's some material in both cases, and we know that the material can burn. So something is burning here, something is burning here also. But I'm asking you about the quality, the property of fire. Think of the property which fire has, because of which, look at this. I mean, it's burning away like houses or buildings and so much. Of course, the house is acting as the fuel, the combustible material here, but property of fire is what I'm asking. So based on the leftover, notice my question. I'm asking you about fire, not about the material. What property does fire have? Because of which here it's... Okay, good. Yeah, so one is its high temperature. Anything else you can think about?
The fuel which we use.
Okay, fuel, all right. But fuel is not the property of fire. I'm asking you about the property of fire. So, like Doris,
okay.
yeah, what? It has very high temperature. What else?
The amount of heat.
Oh, yes. There's a very, very large amount of heat, or we can say energy if you want, because here what we are seeing is also light. So there is a lot of concentrated energy here, high amount of concentrated energy. It has so much energy. It's like one of those uh, sources of energy which is very, very, very potent, because it has the energy is so concentrated. So if we control it, we use this energy for positive purposes for our daily lives. But the same, even in our daily lives, if through some mistake something else in your house starts burning, you had it. I mean, here the fuel is burning, the gas is burning in a controlled fashion. But suppose something catches fire, suppose your cloth catches fire, or something else in your kitchen catches fire, then the same energy, then the same thing becomes uncontrolled, and because of so much energy, it becomes very destructive. So one thing is high temperature, and here SAS team is saying ignition temperature. Let's not talk about ignition temperature, etc. I'm asking about property. So property is like very lots of energy and high temperature. Okay, so this is the major difference in these two cases, which is what I wanted to draw your attention to. So in one case, we are using the same energy in a very controlled fashion. In the other case, we cannot control it. We have to work hard to control it, right? So this is the question I was asking, the same question you can see on the screen. Now, think of early humans. You know, we say that humanity's life changed with fire. Discovery of fire was one of those great advances for humanity. So, till they did not know fire, then their life was different. Fire brought a lot of changes. So, what changes can you think of about? What changes did fire bring?
The utilization of the metals.
Okay. Yes, we could not have utilized metals unless we knew fire. Yes, excellent. What else?
Light.
Light. So, what did humans need light or use light for? The light of fire. Where did they use it?
In dark places during dark.
Yes. So, in dark, humans could light up their caves, even move in darkness. There's something else because of that light and all that they could do.
Scare away animals.
Yeah, scare away animals. Yeah, fire was a very potent tool for protection. So,
Also,
right.
it decreased the amount of time they spent on chewing the food, because the food was cooked, so they could chew it easily and digest it.
Excellent. So, yes, absolutely. It's not only about chewing. We couldn't have chewed, let's say, wheat grains, rice grains. There are so many items that we today eat. We couldn't have eaten them at all if fire wasn't there, unless humans had learned cooking. So they could cook a large amount of things, soften them or pre-digest them. So KSI, I don't know who KSI is, but yeah, I mean, the food was tastier when cooked. Yes, that's also correct. So, I mean, a lot of things became a lot tastier after cooking, especially baking and roasting and all that. So meats also softened, many things softened. Yeah. So anything else which the fire did for humanity? Yeah. What else?
So the question is, how fire changed the way human beings survived after they discovered fire.
Yes, yes. So it brought about many changes for humanity in their lives. So many, some have been mentioned, but there are still more. The benefits, the gifts of fire.
Yes, civilization starts after the invention of fire.
Yeah, civilization started, but in what ways? In fire contributed in
Invention of
ways.
the metal wheels for the transport
Metal.
yeah, casting of
Okay.
metals.
Yeah. So yeah, we've already agreed that metals could be shaped in
Yeah.
different ways. In
The
tools,
desirable manner.
not many metallic tools could be made only when fire could soften metal and actually
Yes,
could
not
beat
only
metal.
metal, even the clay pots also. After it became heated, then they use the clay pot for cooking.
Excellent. See, till we had like only dried clay, it wasn't strong enough. But when they were baked, so we had clay pots which had become solid. I mean, like solid means really strong. So all kinds of pottery actually came after fire came. Yes,
And not
excellent.
only pottery, even the ornaments also. Ornaments they use for making.
Okay.
Then
Yeah.
the yearly man used fire to escape from the harsh climate. During the winter season, they used the fire.
Yes, humans could actually even think about going to cold places once fire was discovered. So, of course, there were other inventions, for example, clothing, I mean, animal skins. But fire was one major reason people could warm themselves, heat themselves.
And
So
they escape from even the wild animals during the night time.
yes, excellent. Yeah. So escape from wild animals. So lot many gifts of fire. When humans got this concentrated form of energy to use, and humans learned how to control it, then their lives changed very, very drastically. So I'll just quickly run through that on my screen. So you can say, you can see seeing in the dark, cooking inedible foods, uh, then potteries, then protection from wild animals, then burning forests for agriculture. I mean, like a whole forest could be burnt down in a matter of few hours. So then extraction of metals from ores wouldn't have been possible. And then also, like Kyle said, shaping them into tools, then keeping warm or even light at night time, hunting. So actually large herds of animals were, I mean, today we will consider it very preposterous, but large herds were driven together and driven to edges of rocks using fire, using torches. So it was used. So fire was a great innovation gift. I mean, not innovation. I mean, like fire already existed, but humans learned how to control and use it. Now, the next question is what you see on the screen. What is exactly fire? We have given some options. Which of these do you think apply to fire? What is it? A kind of element, matter and energy, both, burning gases. Is it matter? Is it energy? Is it a source of energy? Is it a fourth state of matter, plasma? Or is it matter undergoing chemical reaction? Decide.
I think the last option.
The last one,
But
matter
it
undergoing.
could be fifth also.
Right. So Dory has taken the last one as choice. Others?
Energy.
Energy. So Kyle is saying fire is energy. Any other answer?
It cannot be a source of energy, right? Because it needs a so it needs a source for fire to be there. So it cannot be the source of energy.
Okay. I mean, right now I'm ready to take any answer. Yeah. So yeah, this is for so that you can think through the fact of fire being generated and giving out a lot of things. So what is it out of all these? So Kyle, I would encourage your other team members also to answer. So Reshma and Madhavan.
Madhavan, he has gone out for another project now. Only
Okay,
myself
okay.
and Reshma are attending the session.
No problem. So Reshma should speak.
Choose the source of energy.
Okay, so Reshma thinks that it's a source of energy. All right. Anything else? Any other answer? We will explore. We'll explore what it is. See, typically when we teach combustion and flame, we never raise this fundamental question. It is like, what exactly is fire? So any other answer?
It is a visible effect of combustion.
Okay, so you are saying combustion is something else and fire is the effect?
Yes. It is a visible effect of combustion.
All right. So Kyle thinks it's a visible effect of combustion. Yeah, we have to first really decide what fire is. All right. Then only we can go ahead with what it does, and we have to even ask the question, what is combustion? So if there's no other answer, I'll go ahead. I mean, actually, fire is matter undergoing an exothermic chemical reaction. Actually, fire is a chemical reaction. A chemical reaction happening, but who undergoes a chemical reaction? It is matter, what you are calling as fuel along with oxygen often. So, like something, so suppose it's wood burning, so wood and oxygen are combining together, they are undergoing a chemical reaction. But since it's an exothermic chemical reaction, there's a lot of energy given out. So energy is given out in the form of heat, light, at times even sound. So fire will crackle, it will make a sound. So a lot of energy, concentrated energy is given out. But so you see, if you are talking to children who don't understand a chemical reaction, then it won't, then you can't say that this is an exothermic chemical reaction. I mean, depends on the level of children you're talking to. So then you can't use this word, but doesn't matter. You can at least say that it is matter undergoing a change, actually matter is undergoing a chemical change, but even children who haven't studied chemical change won't even understand that. So you can say matter is going a very special kind of change in which a lot of energy is given out, right? So it's matter, actually matter is going through this fast change, and energy is the output of this process. Matter is undergoing a process, right? So and now another question for you. Why do flames have this shape? It's like people say, no, the tongues of fire, tongues of flame. It's like these pointed shapes. And also it's like always shaking, moving. So why do you think it has this shape?
Because it's, I think, lighter than the air.
So what is lighter than the air?
The flames of the fire, that's why they are going upwards, and then they are affected by just direction.
Okay, yeah, kind of you are near the answer, but just think about it. What is burning?
It's liberate, maybe during burning carbon dioxide gas is liberated. Carbon dioxide, water vapor.
So carbon dioxide, water vapor is liberated, but is it because of them, carbon dioxide and water vapor, that you are seeing these shapes?
Maybe the fuel is getting vaporized.
Okay. So what do you mean by fuel getting vaporized? I mean, you're right, but say it in different words, I mean, simpler words. Okay, it's like what Kyle is saying is that it's turning the fuel, whatever is burning is also turning into gas. And that gas is rising and burning. See, the gases will have this shape. No, both of you were actually pointing to gases, but it's the burning gas basically. That's why you see this shape, and that burning gas is giving out so much energy, and I mean, which is heat and light both. So that's why it's constantly like shaking, moving. It's gases. Gases will not remain still, so they are moving. So burning gases are actually rising upwards. See, carbon dioxide is a product of combustion. Carbon dioxide is not burning. Something else is burning, which you are calling as fuel. And that something is taking gaseous shape also. And that's why you see this flame. So it's basically gases burning. Now think of examples of burning. So what products are created? What all is given out?
Carbon dioxide, water vapor.
Carbon dioxide, water vapor. What else?
I have a question in the previous slide. From the
Heat
previous
and
slide
light.
only.
Heat and light.
Yes,
Yeah.
yes. Dori,
So you are saying that a certain gas is being released when the fuel is burning, and that gas is in certain places, but it's rising up and it's catching fire. That's why that's why it's creating that shape.
right, that's what I'm saying. Yes. And actually, Dori, it doesn't seem very obvious. So we will show you an experiment to show that often fuel which is actually non-gas. See, one type of fuel is already gas. For example, your kitchen stove, where you are actually burning gas alone. But it's not necessary that you are always burning gas directly. But even if you are burning a solid or a liquid, it could turn into gas and those gases burn. So this is something we will experimentally show. All right. So any other question? I mean, there's a large series of experiments, but I want to do them only after some preliminary discussion.
No,
So, yeah. Yes, dude.
no questions.
Okay. So I was asking what all is given out. So, I mean, carbon dioxide, water vapor, then Kyle also said heat, light, anything else?
Sound also, ma'am. Sound.
Okay, sound. Yes. What else?
I think it depends on the material of the nature of the material.
Yes, of course. Yeah, but
Leftover undesirable things also, like ash, like the unburned carbon.
yes. So there can be some leftovers like ash and unburned carbon, etc. It definitely depends on what is burning.
Yes.
So, I mean, we have put some things here. I mean, you will see a lot of smoke also, and heat, light, smell, vapor. It's like because there are a large, I mean, there may be many substances burning, not a single one. So, and when vapor can also mean other gases, not necessarily water vapor. So, and smoke also means other gases as well. So, okay. And what do you think disappears when burning happens? What disappears?
Matter in previous form.
Matter in previous forms, all right.
Even the energy also.
Yes. So actually, this question is deliberately to draw attention to the fact that energy doesn't
Nothing
appear.
is being disappeared or nothing is appearing or disappearing. It's just changing its form.
The change in level only. The matter has been changed from one form to another form. The energy level also has been changed from low to higher level.
Excellent. Yeah, we have to remember that neither matter disappears or appears. Same with energy. Both of them, we have those laws of conservation.
Yeah.
See, but here, because there are some teachers here, see, children will not necessarily assume that matter cannot disappear. So, like, if you see, even leave alone children, even humanity, till we understood that gases have weight or mass, earlier humanity also saw that, okay, you are burning a huge log of wood and the log disappears, only a little bit of ash is left. I mean, you burn a 100 kg log and only 2-3 kg ash is left. So you think matter, so people used to think that matter disappears. And children may also think that. So it's like it's important to draw attention to the fact or tell that nothing, neither matter nor energy can appear or disappear. They are just changing their forms. And a lot of matter is going away as gases. So we can't hate, but now we know. I mean, like we all know that some chemists sat and actually measured weights very, very carefully. Lavoisier was one of them. Very carefully, when they weighed everything, they weighed gases, then they realized that no matter was disappearing. So law of conservation of matter also is roughly 400 years back. But law of conservation of energy is even later, like another 200-250 years later, humanity realized that energy also something which just changes form. It doesn't actually disappear. You can't have suddenly energy appearing from somewhere or actually disappearing. It's just changing its form. So that's the idea, deliberately to remind ourselves that these two laws are always applied, are always applying, and it took humanity like centuries, actually millennia, to come to these conclusions. Especially what energy is something which is a very late realization, because energy keeps changing its form. It gets hidden in so many times, so in so many ways that we don't know really, we don't understand what's happening. So these two laws are actually today so fundamental to our understanding of everything. So that applies to combustion and of course every phenomena that we see around. Okay.
So earlier, when people used to burn, as you said, they burned a log of wood and then they discovered that there's only a certain amount of ash left and the rest of it is gone, right? Then how did Lavoisier and all of the other scientists, how did they think about it that like it was gone? How did they know that it was not gone and it has to be
Yes.
somewhere present in the environment only?
Yes. So Dori, this was all done experimentally by very carefully collecting gases and all that. We are going to show some experiments, but our experiments won't be like Lavoisier's, because collecting gases and weighing them is no simple matter. Why is it so difficult to collect gases and weigh them? After all, in principle, I have this bottle, there is air here, so it is collected. But why is it so difficult to weigh?
Because it has very the weight is negligible almost.
One reason is definitely that the weight is very little, but there's another big challenge here. What could be the challenge?
Making sure that the gas that is released from the given reaction, that only that gas is collected and the gas in the environment is not collected, because there is no certain like separation. There's no separation between the gas, right?
Exactly. We are living in a sea of gas. We are living in a sea of air. So everything around gets filled up with air. So somehow we have to eliminate that air, or somehow we have to collect gas, removing that air. Then only you can have a bottle full of gas. And how does one remove air? I mean, does anyone want to talk about how do we collect gases now in a chemistry lab?
The inverted, keeping the inverted beaker in a water, I think.
Yes, we do it with downward displacement of air, which like, okay, Dory and children may not know. It's like you fill this bottle with water. I mean, suppose you have this bottle and you fill it with water and let the gas come in through a pipe and bubble here. Because gas is lighter, it will keep collecting upwards here, displacing water below. So no air can come in, only that gas which you are bringing, I mean, which some chemical reaction or something is bringing, it will get collected here, and then you have pure gas. So like people had to invent this and then do into very careful measurements to realize that gases have weight. Till they knew gases had weight, there was no way of knowing law of conservation of matter. Right? So that's why it's important to remind ourselves that matter and energy are conserved. But here, first, let's distinguish between matter energy and energy. So which of these are not matter? The name is written.
Light, glow, flame.
The
One. Sky, then
No, I don't know about sky. I'm saying light, glow, and flame.
light, glow, and flame.
Sound
But we
also.
sound, okay. But flame we just saw was burning matter.
Oh yeah, okay, sorry, yeah. Light, sound, and glow.
smell,
Right. Any other thing?
Fog. नहीं fog में matter में.
Fog. Fog is not matter.
Glow.
Can you write on the chat box things that are not matter?
I don't know about smell. Is it?
smell is not a matter.
Yeah. So yeah, I want you to think about it. That's why I put it there. So when you smell something, so something must be coming to your nose.
So first I thought that can our senses detect something that is not matter? Then of course eyes detect light, which is not matter. Then smell can be a matter, or it cannot be a matter.
Excellent thinking, Dory. I just want you to think generally what are things we smell. Suppose you have a perfume bottle a little away, or even if you bring it close, or this flower itself. So what transmits from this the perfume bottle to your nose?
The fragrance in the form of gaseous form. The fragrance, the form of gas.
Yes. Fragrance is generally some gas or some particles released which come and hit your nose. So it is, in that sense, it is matter.
Oh, matter. Okay, yeah.
So flame, we decided that flame is actually burning gases. So we will not put flame here. Glow, what you are seeing, and like the STEM team is saying, glow is then would be light. we are seeing these are coal burning, and what we are seeing, the glow that is coming to us is coming as light. So this would not be matter. How about fog, cloud?
Fog is a matter. Fog is a
Fog
matter.
is matter and cloud is also matter.
Dust particles and you have the gaseous state. So it's a matter only.
Okay, okay. So yeah, fog and clouds are actually very tiny droplets of water. So mostly water, but yeah, as you were saying, there's pollution also or dust also. So it's actually matter. How about color and sky?
The sky is not a matter.
Why do you say so?
It doesn't have mass.
Okay, then what is it?
It's just a reflection of my process.
So what is it? It is.
Color reflections maybe.
So I mean, if you want to name the entity, the thing that is there, which you see as blue, what is that thing?
Gases. No, sorry,
Sorry?
water, air, droplets, water droplets.
Yes,
Dori, you were talking about sky.
intense.
Yeah,
So can anyone tell me what is sky?
Scattering of sunlight. The blue color has a low intensity. Maybe it may be the reason of the color of the sky.
Okay, basically it is blue light.
Yeah.
What you're seeing as blue sky is blue light.
Yeah.
It's scattered
Yeah.
and it is entering your eyes. So you feel as if there's something giving off blue light, but it is scattered blue light. So and when you see the red sky, it's scattered red light. So basically, sky is also just light.
Hmm.
So so we see that so many things we are unsure of whether it is matter or energy, but this distinction is very, very important for us to understand the nature of things. I mean, of course, in later years, Einstein comes and tells you even matter and energy are interconvertible, which is another hammer on your head. But then for early stages of learning science, it's better we keep energy and matter as separate. So we come to before we start with we are going to do a lot of experiments. But what is combustion now?
It's a chemical process.
what did we
Okay.
conclude about the sky? Is sky matter?
Sky is just scattered light, blue light. I mean, light
Okay.
of some color. It is just light.
Okay.
Light is scattered all around in that space, and some of it enters your eyes. So you feel as if something blue is there, right? And how and why it happens, we will take elsewhere, not here. But sky is just scattered light. All right.
Oh,
So what is combustion?
It is a chemical process. The matters, the substance which burns in air and just give out the heat and light.
All right. So she's saying, which is correct. We can call it a chemical reaction. We can call it a chemical change. We can call it a chemical process. But I mean, okay, change, we have to say that it is change. It is reaction. So it's a chemical reaction. And so the one substance which we are calling as fuel combines chemically with oxygen. I mean, normally it is like we are talking about combustion with oxygen. Like there are very rare cases where needn't be oxygen, but ordinarily combustion is combination with oxygen to give new products along with release of energy. If you want to call it an exothermic chemical reaction, that's also correct. So combustion is the process. Fire is the burning gases that you see. I mean, because it's giving off light and heat, so you will see fire. It's basically burning gas. But those gases are in the process of undergoing a chemical reaction. They are participating in a chemical reaction. So from here, now we get down to some experiments, which we will show you on a mobile phone. So the mobile phone is like named display here. So on display, so friends, you see the display window and we are showing many experiments one by one. So one is of course the simplest. We have to prove that this candle, when it burns, it needs oxygen. So, and we say that it's combining with, the fuel here is wax, and we say that it's combining with oxygen. So the simplest of course is that I close it. The flame is now actually flickering. I mean, you don't see it so well on the video, but we are seeing it flickering and dying, which means something that this flame needed is not there any longer, right? So, and of course, we will do another experiment related to this, but right now, let me now take, I have a tube which is open at
पापा
both.
से नहीं होगा तो डाल रहे हैं.
Okay, somebody's mic is on, so I'm showing a tube which is open at both ends. So if I put this tube on the flame, on this candle, do you think the candle will keep burning or will it extinguish?
Yes, it will keep burning.
It will keep burning? Okay, let's see. So I am putting this tube over the candle and the candle goes off. The tube is open from top. See, the tube is open from top, but the candle still went off. Why do you think this happened?
The absence of oxygen.
Absence. Why there's an absence? It's open from top.
There's only available oxygen already that candle used for lighting. Then if there is no more oxygen, then the flame.
But Kyle, the oxygen could have entered from top.
I think it took
Already-
too much time.
Kyle, just a sec. Yes, somebody else is speaking. Yeah.
Okay.
I think it took too much time for the oxygen to reach.
Okay. So there's one answer that oxygen from top could have come, but there's a long way off and the oxygen cannot come. Actually, we don't have a shorter tube. We have the top part of a lantern, which we'll be using, but anyway, right now, okay. So he's saying that it took a lot of time for the oxygen to reach, so it did not burn. So we'll do another experiment.
So
See, these
if you, yeah, sorry.
Yes. Yeah, tell me.
So if you would have used a smaller tube, then if you don't have it right now, what would have been the result?
See, we don't have a smaller tube, but we have that lantern top. We'll put it here. So we are using a lantern. Actually, a smaller variety is also available. We couldn't get it. Kyle has it. I mean, the STEM team has. But anyway, here.
So I think what Kushal said is right. It was taking a lot of time for the oxygen to reach the candle when there was a longer tube.
Okay, maybe. So here we see that when we put a broader tube, it keeps burning. Okay. So maybe now it is getting its supply of oxygen. So therefore it's burning, but we'll show you another thing.
But it leaves smoke, no, ma'am? When you use the Latin,
Then what happened?
it leaves smoke.
Yeah, so when
Side of the Latin. Top.
if it releases smoke, then I mean we have to ask the question why it's releasing smoke, but right now it wasn't actually. It
Okay.
wasn't releasing smoke. So Kyle, my request is no pre-generated answers. And if you already know some phenomena, you have to give a chance to at least children to interpret it and say from their side, right?
Okay, ma'am, okay.
So
Now,
when you put the lantern on top of the candle, you change two things. First, you change the width of the tube and you change the height. So we don't know whether the height has any role in burning of the candle.
excellent observation, Dori. Yeah, I'm changing two things together, but I did not have a shorter tube. That's a constraint. But anyway, I'm showing you another experiment where I will use the same tube, the long tube, but the only change I'm making is now I'm putting two eraser here. I mean, any two supports, and the long tube now I'm keeping on the support. We'll have to hold it.
It will keep burning, I think.
Why do you think it keeps burning?
Because the hot air is rising up and the air is when the air is rising up, there's empty space, and to fill that empty space, more air is coming from like the bottom of the tube to fill that space, and thus oxygen supply is continuous in this setup.
Yes, very nice. It is like, this is called the chimney effect. Chimney effect is exactly this, because of heating, hot air rises up. So we have to somehow allow the hot air to rise up and fresh air to come in, and therefore a space below gives a good chimney effect. Though we have an experiment to show it another way, but right now, I mean, I will try if I can show the movement of air using a little smoke from an agarbatti. Oh. Agarbatti is a good device to show the flow of air. Let me see if we can see it. No, not visible actually, not visible nicely. I was trying to see if the smoke will show us, but there's not enough smoke. No.
Can you use 2-3 instance
There. We just saw. I mean, can you see the agarbatti smoke rising up?
Yes,
Yeah.
So it is actually showing us the flow of air. There is another experiment we do. If we create a partition, so if we create a partition in between,
Is it possible to trap the smoke inside the tube and keep the tube closed from the bottom, like remove the blocks?
See, let me see if we can keep a partition here. See, I am putting it's become very hot actually. And we are putting a partition in this tube and trying to, but it's becoming, the whole tube has become black. But if we keep a partition, I think the partition is small, but anyway, let's see. So then, for this partition to work, we'll have to remove the two supports at the base. The two supports at the base are removed, but we have kept a partition. And now the candle keeps burning, but firstly it starts giving a lot of smoke. But it burns, though with a lot of smoke. And now let me put an agarbatti and let's see if we can see the direction of movement of air. No, it's giving too much smoke. Let it be.
There's a certain condition in which the candle has to be when it produces the smoke.
So we are trying the partition experiment using the lantern. But anyway, you were asking a question, Dori?
Yeah, there has to be a certain condition for the candle to produce smoke. It does not produce the smoke when it starts burning normally.
So, I mean, why do you think the candle starts giving so much smoke in, for example, you saw just now, no, the moment we covered it, covered as in the tube, when we removed the base, the supports, which means we did not allow air to come in from below, then it started smoking a lot, which Kyle was saying actually earlier. But now I'm asking you, a lot of smoke indicates something. What is it indicating?
Lack of oxygen.
Yes, actually it is incomplete combustion happening. A lot of smoke, black smoke means, which we will see later. But
Okay.
right now we have a partition here and so Manisha is now has started the candle. The partition has to be kept in such a way so that it doesn't touch the flame. If it touches the flame, it starts burning itself. Just a second. So now let me quickly try showing the direction or movement of air using an agarbatti. Can you see? Is it visible? No, it's not visible.
No, it is not.
Actually, we are trying to show that this agarbatti smoke, actually agarbatti is not giving too much smoke. Agarbatti smoke is going downwards from one side. It's going in. Okay. And coming out from the other side, not a little visible to us, may not be visible to you. I mean, we can see it little, but not very well visible. Here, because of the partition, what has happened, the chimney effect is created in another manner, which means that fresh air is going in from one side and escaping from the other side. So basically, I mean, chimney effect means this, that some place for fresh air to go in and some place for hot air to go out.
But the hot air will come out from both the sides. Why is it creating a chimney effect now?
See, the thing is, it's like, this is what it's choosing to do. It can come from both sides, but because there is a candle burning, there's inflow and outflow. It's become hot. But see, the candle is continuing to burn. It burns in otherwise also, but here no, let it be. It's not very well visible, so we'll let this experiment be. Instead, actually, I want to show.
So anyway, we saw we saw the need for oxygen, whether oxygen is coming from below or wherever. So then we come to that famous experiment, which is done, which we will do after putting some water here. And we will make the water a little colored. So here's the burning candle. And I close it. So the question is, why does the water rise? Any answer? Why does the water rise?
Because it draws out oxygen from the water.
Okay. So you are saying that the candle consumed the oxygen, and inside the glass, since the oxygen was exhausted, the water rose up.
Yes.
Okay. So this is Dory's explanation. Does anyone else want to say something here?
The particle inside the closed container expand and contract.
Okay. So
How?
firstly, a particle doesn't contract or expand. So please don't use the word particle here. What expands or contracts?
The gas inside the particle.
Okay, so you are saying that the gas inside expands and contracts, and then there's another answer. Let me just see the chat box. Heat. See, the person who has written heat, please explain what you mean by heat or what heat is doing. Because of pressure difference. Ankita is saying because of pressure difference. Ankita, you have to explain what pressure difference where.
Can you do this once again?
Of
I
course,
just
of
want to
course.
see whether the water is rising after the candle blows
Okay.
off or during.
Sure, we'll do it again. This is one of the most controversial experiments in Indian education system, and it has competing explanations. That's why we think that it's important to show. So, okay. So here's our candle, and now we cover it.
Okay, yeah. So, for first few seconds, the candles, so the candle's flame is diminishing, but the water keeps rising. The water starts rising and it keeps rising. So I think because it requires oxygen from the water, it could be because agreed. It could be different things.
So Ankita has said as oxygen is exhausted, it creates a kind of vacuum inside the glass to balance the pressure. The water enters. So, and Dory is saying, Dory, your explanation is, say that once again.
I'm actually confused whether the candle requires the dissolved oxygen from the water or not.
Okay. So the thing is, see, don't be surprised.
That's what I have been like. I have been told by different sources, but I don't know.
I'm glad that you are saying you don't know. At least it's good to make guesses. But the interesting thing is about this experiment, like for 60 years or okay, 70 years, Indian system has been saying various things about this experiment, including textbooks. So even the textbook explanations don't agree. So anyway, so we will show a variation of this experiment. Actually, this experiment should be done with multiple variations. So now this time we'll do another variation. So, okay, one explanation says that the oxygen inside is exhausted, right? And how much oxygen is there in air?
21%.
20%. Okay, 21. So yeah, so roughly one-fifth air is oxygen. And so one explanation says that inside oxygen gets exhausted and therefore the water rises. So we will do this experiment now with 2 candles. 2 or 3.
So now you're saying that there should be so whatever the volume of the container is, there should be 2/5 rise in the beaker of water. Like for the water 2/5 rise on it.
I'm not saying it. I'm saying people say it. So here we have 3 candles, and now I actually this time the first 2 candles actually got extinguished too fast. I'll do it again and add some more water. We are trying to keep shorter candles because if the candle is too long, it can't get, it gets extinguished by the top of the glass itself, so which is not what we want. And we don't have a taller glass than this. So now we have 3 short candles and we will light them. Do you see the level of rise? Which is much more than last time. Actually, it can go up to half. I was trying to do that, but didn't go up to half. But surely
there
this
were 3 candles, right?
Yeah, but then see, 3 candles doesn't mean that the amount of oxygen has increased, right? See, the explanation, if the explanation of oxygen was correct, then whatever be the number of candles, we should have water rising only by 1/5.
Yeah.
So this is not a 1/5. This is certainly more than 1/5. Easily more than, it's about 1/3 now. So, and here somebody is saying carbon monoxide will also be there. Ankita saying many candles will turn off quickly. Yes, of course. The thing is, I want you to respond on, is it because of oxygen getting exhausted? Yes or no?
Yes.
What do others say? No, I mean, oxygen will get exhausted inside, that's correct. But is the water rising because of oxygen getting exhausted? If so, how will the water rise to a greater height in the second time when we increase the number of candles? After all, oxygen cannot become more than 1/5.
Maybe I think it's because of both the reasons that the candle is exhausting the oxygen, that is why water is rising. And second, the candle is using some of the dissolved oxygen, or not dissolved, in some way it is using the oxygen present in the water to keep burning.
Okay, so let me give you one piece of information that oxygen does not dissolve so much. I mean, if oxygen could dissolve so much in water, we will not have oxygen left in the atmosphere because there are enough water bodies around. Oxygen dissolves only to the extent of 4% in water. So only little water, and whatever water we have here will already have dissolved oxygen. So oxygen, or for that matter, any other gas, won't dissolve to this extent, right? So firstly, dissolution of gas is not the explanation. But then the question arises, what is the explanation? Anybody else has anything to say?
The pressure difference inside the beaker and outside the atmosphere. The pressure
So
difference.
how did that pressure difference get created?
Then once the flame switched off, the pressure inside the beaker is reduced in order to compensate the pressure.
Kyle, there is no point giving pre-generated answers. Why would pressure decrease once the flame goes off? When the flame goes off, why would pressure decrease? I'll get back to my laptop.
Yes, gas start to contract. Once it starts to contract, the pressure automatically decreases.
My question is, why would pressure, see, first, there is flame inside, there's a lot of heat inside. So, so actually, gas should expand, the gas inside should expand, isn't it?
Yes.
So if the gas is expanding, then the water will not come out.
Due to increase in temperature inside the beaker, the particle starts to move randomly and hit the containers. Automatically, the pressure increases.
Yeah, so pressure, okay. So inside there's a burning candle. So
Yes.
because of the heat, there's lots of movement of air. If you
Kinetic
forget
energy,
the, I'll be more happy if you forget the particles and the kinetic energy. I mean, right now, the gas inside, because of lot of heat, the pressure will expand. Pressure will increase. Yes. Now what happens?
Then once flame switched off, automatically a contraction of the gases happen. So the kinetic energy of the particles reduced. Automatically the pressure is also reduced. So you know that the pressure.
So let me show you the fault in this explanation. Right. That's why I'm saying that.
Yes, ma'am.
Not good to memorize explanations given elsewhere and think that that is the correct answer. See, okay, the glass inside has some air, and which is filling up the whole glass, right? Now, because of heat, that air expands, and then the same air contracts. There's no empty space created that way. What you are saying, there will be no empty space created that way. So that is the fault in your argument. Then I am asking the other argument, which is given in textbooks, that oxygen gets exhausted and therefore the water rises. What is the fault in that argument? Meanwhile, friends, while you are answering this, let me prepare some lime water. Just give me, actually, I should have done it earlier. I have here some chuna, I mean, which is put in pan, beetle leaves. What do you call it in Tamil, or I mean in your region? We call it chuna. This is essentially calcium hydroxide, also known as slag lime. But anyway, this we got from a pan shop. I will put a little chuna inside this bottle.
In Tamil, it's called Sunnambu. ma'am.
What do you call chuna?
Sunnambu in Tamil.
Okay, okay. So this is that. I mean, I didn't capture the word very well, but that's all right. You know what I'm talking about. So I have put some.
Sounds similar to Chuna. Sunnambu.
Okay. See, there are two kinds of tuna. One which we call as, I mean, it's also called quick lime, which is used for whitewashing. So that actually starts doing a very fast reaction with water. It starts almost boiling. That's in these parts we call it kacha tuna, but that's calcium oxide. Once you make it react with water, it becomes calcium hydroxide. So, but this is already calcium hydroxide. See, it will not react with water. I'm just going to put some of it inside this bottle. I'm actually trying to create lime water. I should have done it before because it takes a little time, but that's all right. So I have put some tuna here, calcium hydroxide, put some water here, and I will shake it a little so that it dissolves and leave it to settle down a bit. Actually, the calcium hydroxide is not very soluble in water. It is mildly soluble. So some of it will dissolve, rest of it will settle down. And I want a clear solution of dissolved calcium hydroxide, which is which we call as lime water. So that's what I'm trying to make. So I'm putting in water here. It's currently milky, but I don't want it milky. So I will kind of shake and leave it to settle down for some time before we can do our rest of the experiments with lime water. But coming back to our candle experiment.
Yeah, I have
First-
one thing. Okay.
Yeah, please carry on.
Okay.
Yeah.
So first when you demonstrated the experiment, first thing that came to my mind was that the candle needs more oxygen, and so it's drawing the oxygen out from the water. But then you said there's not enough oxygen dissolved in the water for the candle to burn, right? So there's some other reason why the water is rising.
Yeah, another thing is, even if suppose there was enough water, oxygen in water, the candle cannot extract it in any fashion.
Yeah.
It cannot.
Yeah. Okay. Now the second thing is the oxygen that was there in the air inside the beaker, that is getting exhausted, which is creating, this is what I think, which is creating more space. And so to cover up that space, the water is coming up in the beaker. That could be one reason.
Okay.
Is that
so? Okay. Yes. Carry on.
Is that why the water is rising? But then you said that since the temperature is increasing, the volume of the air is increasing. So the beaker mein whatever the empty space is there, it's being covered by the air only because it's expanding. I think, I don't know.
Yeah. So see, if this was happening because of the oxygen getting exhausted and water rising, if water was rising because of oxygen getting exhausted, then water could not have risen further. If I put two candles or three candles, then it cannot rise any further. But it actually rises this time about one third. But you can actually make it rise up to half or maybe more. I mean, like quite a lot. And we made much more. So the oxygen explanation actually doesn't work. So the question is, what happened to the oxygen thing? What happened? Anybody here wants to say that oxygen got exhausted? All right, the candle will take oxygen, but what will happen to why is this explanation not correct? There's another thing. Often textbooks have also written this for decades. And even now, that day, Kyle showed me the NCRT workbook, which is currently in use in Pondicherry, and it wrote exactly this, what Dori just said, that oxygen gets exhausted and therefore the water rises. But what is the problem here? Anybody here? Can you say what is the problem in this explanation? Dori wants to say. Okay, Dori.
You just told now that if that was the case, then it would have risen only 1/5, but it's rising more than that.
That I said, but I'm saying is, I mean, why isn't it, why is the 1/5 place also not getting emptied because of oxygen? I mean, I have already, Ankita is also saying this, the water would have risen to the same level, even if we put more candles. But even in one candle's case or any candle's case, it's not exhaustion of oxygen. Why? Because something else is there which we are completely ignoring. So can anyone think about that?
Volume of the gas is increasing because of the rise of the temperature. But then
Volume
why
of the
is it increasing water? I don't know. Why is water increasing?
that other explanation. But firstly, my question right now is, see, when oxygen is getting exhausted, something else is also happening at the same time to fill up that space. I'm giving you a hint. That space will be filled by something else. What could that something else be?
Carbon dioxide.
Exactly.
Yeah, okay.
What will happen to the carbon dioxide? Yes, exactly. There's carbon dioxide also generated. See, because wax is a carbohydrate, so there'll be some water generated, which means some water vapor generated, some carbon dioxide generated. So, okay, we can assume that the water vapor condenses, but even if you assume the water vapor condenses, what happens to the carbon dioxide? It will still fill up the space. So this explanation is completely wrong. And what is actually sad is that this explanation is still going on in sometimes Indian textbooks or sometimes in verbal conversation. I mean, generations of textbooks actually ignored this because somebody wrote it once and everybody copied. That's what happens in textbooks. Everyone copies from some original textbook. So one mistake made keeps getting replicated for generations. But thankfully, by now, this experiment has been discussed a whole lot in so many circles. I have myself seen this getting discussed, and I'm surprised that still an NCRT workbook, not the book, not the main book, but the workbook still has that explanation because somebody who must have prepared that workbook again ignored. Yes, so here Ankita is saying that volume of CO2 will be same any number of candles. Yeah, so any number of candles, volume. See, if carbon dioxide is occupying that space, some space, which will be definitely equal to oxygen, then okay, maybe not equal to oxygen because some water vapor will also be generated. But the thing is, carbon dioxide won't increase because of more candles. So something else is happening. So this oxygen and carbon dioxide explanation doesn't work. So what works then? So Kyle was actually close to the answer. But the thing is, Kyle, this is what happens if you have heard the explanation from somewhere and repeat it. It's like you have to think by yourself. See, here's a candle. The candle is giving off a lot of heat. What will happen to the air around it? Currently, the candle is not covered. Candle is burning. And what will happen to the air around the candle when there is a lot of heat?
It will be hot. It will be warmer than the air surrounding.
Sorry?
It will be warmer.
it will be warm. So what is the nature of warm air?
The warm air raises up. The warm air raises up.
Is
It raises up.
it rises? Right,
Yeah.
correct. So around the candle, much of air has risen up. And what is the nature of air surrounding? Just think of the candle flame. What will be the nature of the air surrounding this?
It will try to occupy that place.
See, air will always occupy the space, but this
Air will be heated. Air
yeah,
will
it's
be
heated. So because of heat, this air, and what will be the difference between other than
The
heat?
colder.
This
Maybe
air
the surrounded
and
air
other,
is colder.
sorry?
It's cold in nature. The surrounded air is cold compared to the air above the flame.
Air. Heat.
I can't hear. Can you write, please?
Around place are heated. Air heated.
Yeah, air is heated. So because of heat, what will happen to this air? This air which is around the flame. What is
Around the air are heated. After closing there, air will be cold, cooling.
that?
Yes,
That is correct. Yeah, but
Yes,
I'm saying because yes.
cold. The air is first time air is heated. Then close the speaker. Air is cold. Some places occupied, some places gap.
So yes,
Occupied
the
places.
first you are right. You are saying that first time it's heated, but later on when we close it, then it starts getting cool. I agree. But because of heat, what has happened to this air?
Air is explained. Air is explained.
Air is expanded. This air has already expanded, which means it's thin air. Thin mean here what we mean is it has low pressure, low density. It's like any air around this. See, you are saying it's rising up. Whenever it will rise up, there'll be fresh air coming in. See, so rising up doesn't mean this place will become empty of air, only that any air which is around the candle is actually expanded air. You call it expanded air or low pressure air, call it thin air. It will have less density because it has low pressure because it is already very expanded. And then this region around the candle is already filled with very thin air, which means low density, low pressure air. And now we close it with the bigger. So the inside oxygen gets exhausted, carbon dioxide gets generated, the candles go off. But now there was this thin air. What happens to this thin air now? The hot, thin air. What will happen to this hot, thin air?
Does it get cooler now?
Yes. The flame was like bursting with giving a lot of heat. Suddenly that heat goes away. And this expanded air, and there's also water nearby. Of course, there's air nearby everywhere. This air now starts contracting. In fact, it contracts pretty fast. It was like very thin air, and suddenly it starts contracting, and there's this blank space created. It's like partial vacuum created. Call it partial vacuum, but this air contracts, and immediately there's this blank space is filled with.
You are on mute.
Yeah. So the water now rises up to fill up this blank space because there's from outside it's being pushed. I mean, we talk about that in air pressure, that there's external pressure pushing water in, so that this water rises up and fills up whatever blank space is created. Right? So that is the explanation. See, I deliberately took this. We normally don't take this in this session, but I realized when I saw that workbook, I realized that this experiment is almost always it goes on with a wrong explanation, even in textbooks. And that's why it's very important to clarify. There's another variation to this experiment, which we'll not do just now. I'll just tell. See, we are saying it's contracting and cooling. So you can stop it from cooling. How can you stop it from cooling? Suppose you want to test that it's actually contracting because of cooling. How can you stop it from cooling? Remove the jar. No. Removing the jar will, which means all the place will be filled with ordinary air. So there our
Can you
experiment is
repeat your
gone.
question?
My question is, suppose, say, I am saying it's the air inside is cooling and contracting. So if we want to test that it's actually cooling, can you stop it from cooling? Can you do something which will not let it cool?
When you heat,
Surrounding place are heated.
again heating. By
Sorry?
heating, we can.
How will you heat? See, you have to now not let the air inside cool down. So what can you do?
So the air inside the beaker, which was warm, it was warm, and then as soon as the candle blows up, it starts cooling. So there's already heat in it. How will it start contracting and cooling so fast? Is it because of the cold? Is it because of the water? The temperature of water? Is it helping in its cooling?
Some temperature of the water, temperature of air, surrounding air also. So it will cool because suddenly so much heat which was coming from the candle is not coming. The candle has gone off, and their surrounding air is cool. Water is cool, so it will have to cool down, and because it cools down, it contracts.
Yeah, but
my
what I
question is,
don't understand is how will it contract so fast? Why will it contract so fast? It will contract slowly.
the thing is, see, okay, if why will it contract so fast? I suppose you'll have to actually do some actual measurements. See, in like as you go ahead in learning physics, you will read about gas properties and gas laws, which actually relate pressure, volume, temperature. So if you want to actually without careful measurement temperature inside, previously, later, all that is possible. I mean, we have thermometers, which digital thermometer, which we can actually put in a small stylus. I mean, something like a wire inside, and actually measure the temperature and all that. So, yeah, but this expansion and contraction of gases can happen pretty fast with temperature, expansion, contraction, and all that. So, but why is actually the nature of gases? Gases do expand, contract. I mean, like liquids and solids behave completely differently, and gases behave differently. So that's kind of different here. But I was just asking, can you stop it from cooling? So I'll just tell the answer. See, we did it in one class where we poured hot water on the beaker, which was cooling. We poured hot water. See, students came up with this answer. We poured hot water, and the beaker could not cool. The gas inside could not cool, and no water no water raised up.
So when do you pour the hot water? After the candle is it's blown up?
Yes. The moment the candle blows off, you pour hot water and no water rises. So basically, you're not allowing it to cool.
Okay.
So you can
But
see
but then after some time, the water will rise because after some time it will cool.
Yeah. So I mean, see, you keep pouring, then it will not rise. You stop pouring, it will rise. Like basically, contraction of inside air. And I'm telling you these different variations of the experiment because all this can be tested. You can test your hypothesis. Your hypothesis is that it's contraction of air which is making the water rise up. So you don't allow it to contract, you pour hot water. So, well, I mean, people keep thinking of variations of this experiment because this experiment has gone through endless discussion. There's enough on the net also. If you give a search on this particular experiment, you will find loads of discussions and various variations people try and all that. People do full workshops on this experiment alone. So, which is not what I want to do. I want to actually get into combustion. And my lime water is not exactly ready. So, I wanted to show you the generation of carbon dioxide also. But we'll do, meanwhile, we'll do the setup of another experiment because that experiment takes a little time, but it's a beautiful experiment. I'll set it up right here, right? I mean, which means on my, in front of my laptop. Touch three, plate, green water. ये लाल वाली कटोरी आयरन फाइलिंग्स 1 चम्मच. So this experiment, see, it takes a little time. So I'm doing it in front of you and we'll wait for it to. So see, I have this plate in which I'm pouring some water and I've just colored it because so that it's easier to see. And I have put this bowl. In this bowl, this is iron powder. So I'm putting some iron powder here. This is the experimental setup. And the thing is, I want this iron powder a little wet. So I will pour a little water here, little water, and mix it so that it's a little wet. And some of you, particularly chemists, will be able to make out what I'm trying to do. There's iron, there's some water, and of course, there's air around. And now, जो बड़ी वाला glass है ना, ये नहीं बोला लंबा glass, वो वाले. So iron powder and little wet. There's water here and I'm covering it with this glass and you can see how much the glass is, how much water has risen in this glass, right? You can see with the color, right? And we'll wait a little, wait for a while. I will shift it here. Till then, we'll get into our other discussions. Till my lime water is getting ready. ये lime water को भी ना एक गिलास में डाल देते हैं, मतलब ना ठीक से settle हो जाता है. I want the lime water completely clear. We'll put it in a beaker and cover it. Lime water should be in a colored. Cover it. Okay, so while the two experiments are on, we will go ahead with. So we saw many experiments with oxygen. Now we can, but carbon dioxide we'll be able to do only when our lime water is ready. It's still not settled. It takes some time. So till then, we'll go ahead with our other discussion. So see, it's like people had about combustion, see the discovery of oxygen, discovery of carbon dioxide, and combustion is a combination with oxygen. All that took time, I mean, there was this story or theory of phlogiston. Actually, scientists earlier used to believe this, like about more than 200 years back. And this was actually demolished by Lavoisier, Priestley, some of those chemists. So earlier people used to believe that anything that burned had a fluid called phlogiston in it. So if something burned, the phlogiston, the thing which burned, for example, wood is burning, so wood is phlogiston rich, and when it burns, it releases its phlogiston to air, which is actually lacking in phlogiston. So it's phlogiston going from one thing to another thing. That's what they thought. So, and some things were rich in phlogiston, some things were poor in phlogiston. That was the belief. But the problem with this theory was the theory started, I mean, this was a great belief, and initially it seemed like this was a correct explanation of burning. But the problem came with metals. When metals burned with a flame or without a flame, but metals interacted with air outside, then metals actually gained weight. Instead of losing weight, I mean, things like wood, etc., would reduce in weight very drastically and will turn into ash, but metals actually gained weight, which was very surprising. If metal was losing its phlogiston, why will it gain weight? So and not only metal, I mean, this is one experiment done by Lavoisier. He burned phosphorus. So he's put phosphorus here in a bowl, which is called a crucible, in a small bowl. And he burned it using, actually, he used to do this so that not to disturb anything inside. He would burn it concentrating sun's rays on this. So he would concentrate sun's rays. So when he concentrated sun's rays on this, the phosphorus burned, and then phosphorus would change into something else, which today we know it's oxide. It would be oxide. But when it burned, it actually gained weight. So the phlogiston thing could not be correct, because why would it gain weight? If it would burn, phlogiston would go outside and it should lose weight. So that's why, it was careful, very, very careful measurements, which led to the realization that, okay, phlogiston theory isn't correct. So metals gained weight. And then there were these very interesting experiments done by Priestley. I don't know whether he's called Priestley or Priestley, but see, look at this beautiful experiment. First, he put a mouse inside a jar, glass jar, and inside burned a candle. So the candle got extinguished, like our own candle did just now, but also the mouse immediately became unconscious. Today we know the reason. The oxygen is finished. They did not know about oxygen. But he realized that something in air has gone away, has got finished, which is important to sustain life. And that's why, since that thing is not there, therefore the mouse has become unconscious. So One thing was establishing that some part of air sustains combustion, but it also sustains life. So the same thing is being utilized by combustion, same thing is being utilized by living things. And interestingly, when the variation of this experiment in which a plant was kept inside, then the mouse kept living. Even if the candle also kept burning, even if the candle was inside the jar, the mouse was inside the jar, and there was a plant. So both the things kept happening. The combustion kept happening, the mouse kept living. So the same thing which was inside air, which was required for burning as well as life, the same thing was being given out by plants. So plants were giving it out and others were utilizing it. So through this beautiful early experiments, this thing was slowly realized. So Priestley also did an experiment, mercuric oxide, where he actually took some mercuric oxide in a bowl, burnt it or heated it using sun's rays. So the candle did not get extinguished. The candle kept burning. So which means mercuric oxide, see, mercuric oxide name is a later name. I forget what was the original name, but this powder, so this powder was giving off exactly the same thing which was needed by the oxygen, by the candle to keep burning. So this was releasing that chemical, that thing, that gas. So some part of air was that gas which sustained burning, sustained life, and this powder was also giving it off, was what Priestley established. So Priestley and Lavoisier are two very important people who built this. But of course, there were many others. I mean, these early chemists did a lot of experiments. Now look at our phone experiment. The setup I just did. Can you see? It's not so visible on camera. Maybe we'll show it with the water has risen up to here with green color. Can you see? Otherwise, we'll show it with the mobile
No,
phone.
it's visible
Because,
that water has the same level as it was in the beginning.
sorry?
To us, for me, it is like as it was as like in the beginning.
We'll just show it on. See, the water has actually risen right up to the top of this bowl, and soon it will start pouring inside the bowl. Actually, the bowl will get filled up with water. So the iron inside, there was only iron with a little water. Something is happening inside because of which now the water is rising. Now there is no effect of any heat, any candle burning, nothing, but the water is rising. And it will keep rising. Somehow this bowl did it very well. So I chose this bowl. I tried with other bowls also. But I'll show you after a little while also, the water will go inside and fill up the bowl. So why is the water rising now? It's a beautiful experiment, worth doing. But the question is, why is water rising this time? Anybody?
No idea.
Iron oxidizing. So Tripti is saying iron is oxidizing, which means, Tripti, for the sake of children here, you have to explain what you mean.
So some reaction is happening with iron and water inside the beaker. Is that what's happening? Due to which
So,
something is being released?
okay, so some reaction is happening, but it can't be only with water inside because, see, water rising inside this glass is indicating that space inside the glass is getting a little exhausted. There is this glass, it had air inside. Now that some space inside is getting reduced. So that means whatever is happening inside is actually utilizing something inside air.
flame training சீக்கிரம் ஆர்டர் பண்ணுங்க காமாட்சில இருந்து.
But uh, this time the exhaustion of the gas is not due to difference in pressure or temperature, right?
Exactly. So that means something is consuming that gas. So what is consuming that gas?
But how can the gas be consumed? If something is consuming it, it must be releasing some other gas.
Not necessary. Not necessary. See, when
Here
That's why
iron
we-
combined with oxygen and gives iron oxide. It consuming the oxygen present in the air. Only oxygen.
Yes. Yes. So that's what, yeah. So as Kyle is saying, as Tripti has said, the oxygen inside the air is now getting combined with iron. The iron is actually rusting. It's making its oxide. What is surprising is that this starts happening very fast when you make the iron a little wet. Rust is a compound which forms only in the presence of water. So that's why this powder, till it was dry, nothing happened. But the moment we put a little water with that powder, so iron starts making its oxide. So you see, I was showing the same experiment by Lavois here, no? I mean, so see, now the water has started going inside the bowl also, and maybe we can show. I'll lift. See, it started making the bowl wet inside. Can you see? Water is going inside the bowl. So after some time it will fill up, which means iron is quickly utilizing oxygen inside, turning into iron oxide, which means it's rusting. So rust is also, you can call rust as slow combustion. Rust is also combination with oxygen. The only difference is here, this is iron oxide, which is also a solid, so it will remain here. In the case of carbon dioxide is a gas. So the gas fills up the space. Here it's not a gas. Here it's iron oxide, a solid, which it will remain inside the bowl. So therefore, there is blank space being created. Look how water is filling up. I mean, this experiment was a revelation. In fact, there's another variation of this experiment, which another science resource person, Raman Swai, he did it with steel wool. So we will order steel wool. Right now we didn't have it, so we did it with iron powder. There you can keep I mean, you can take a conical flask, take some steel wool, wet it a little and put it inside the conical flask and invert the conical flask on a plate of water. Plate the way we have inverted the beaker. Take a plate, put some water and invert. After some time, the water starts rising. And the steel wool is up there. I mean, in the conical flask. I mean, I can draw and show.
What is steel?
Yeah, steel wool is actually basically like cotton wool. It's steel fibers. Earlier it was used a lot for cleaning, now less common, but it's available on Amazon. So, I mean, it's like you have to invert this. This is suppose your plate filled with water. And this is your water. And this is your steel wool. So the only thing required is that steel wool has to be made a little wet. And the water starts rising. I mean, I couldn't, once when I saw this, I couldn't believe that rusting can happen this fast to actually consume the oxygen inside. But water starts rising here.
Ma'am, how long will it take, ma'am? I have one doubt. How long will it take? If you just keep the steel wool,
not in 10 minutes.
Okay.
See, how much time did our experiment take? The one I did, not even 10 minutes. It's very fast. Yeah, and it's an amazing experiment to show.
Can we use the steel wool that you use for utensil cleaning? Can we use the steel wool?
See, that one, the one which we get, which it doesn't have thin threads of iron, no? That one has thick.
Okay, same
So
like thread like structure.
But you can try. See, it's good to try various things. I tried iron powder. The iron powder has a lot of surface area. See, even steel wool has a lot of surface area. So the reaction happens nicely. So with that one, the one you get for cleaning the utensils, I haven't tried, but you can try, of course.
Then
we should try.
Okay, you can try with a piece of iron bar.
Sorry?
A piece of instead of the iron wool or instead of the iron powder, can we try this experiment with a piece of iron bar?
Piece of iron bar will not work. We'll soon come to that also. Actually, we have an experiment related to iron nail versus iron powder. We'll come to that, but it's already 1 p.m. So the session was supposed to be 2 hours. See, we can go on for some time, but because we're having a lot of discussion and experiments, it's taking time. So we can carry on for some time, but still will not be able to finish today because we have many experiments left. So maybe we continue tomorrow. One possibility is we continue tomorrow. Other possibility is, I mean, we continue just now, but I doubt if we'll be able to finish. Let me just check how much is left. There are many things left still.
Tomorrow, which time, madam?
I mean, we can come between 11 to 1.
Okay, ma'am.
And only if everybody is ready, or even today we can do late, like let's say afternoon after lunch or something. If everybody is ready, we can do that also. Say 3 to 5.
Today also okay, madam.
See, it's fine, then we'll do it today because today Manisha and Parul are here to support. And we have spread our office around with all this material. So it's easier. So if you are fine with it, so then everyone has lunch, take some break because, you know, a webinar when it goes on continuously becomes a little heavy. That's why some break is a good idea. So say 3 to 5. I mean 3 to whatever time.
Okay.
Okay, madam. Okay.
Yes,
After
then
3,
we'll
madam.
Yeah, 3 onwards. So if there's somebody who's not comfortable with that, please say so.
I actually have a class from 3:30 to 4:30. But I can see if I can
Tomorrow, So tomorrow we were planning to keep a session in Hindi for Nanakpata children from 11 to 1. So we'll have to postpone that if we don't do today. If we do tomorrow. So if everyone is okay, then we'll have it today. Also because like when we do it in our office and there are a lot of experiments, then like the office team who's doing it. So see, everyone has to say, okay. I mean, if there's somebody having a problem, I mean, Tori, can you manage 3 to 5?
Okay, madam. I am okay. Arakonam Padmanabhan, madam.
So only Dory has raised objection. Dory, what about you? Kyle is all right.
So I'll see if I can reschedule. I'll have to talk to the teacher, but if I miss the session, I will watch the recording.